So let's talk about calorimetry. Calorimetry is the field of chemistry specifically dedicated to figuring out changes of enthalpy. And to do this, we use what's called a calorimeter. Now, what a calorimeter does is that it isolates both the environment and the system from the rest of the world. So this way, all the energy contained in both the system and the environment are localized. They can't exchange any energy with the rest of the universe. Now, when we do calorimetry, we break the world into two parts. First part is the system. The system is what we're interested in. Usually there's some unknown parameter we want to use, like or figure out like the heat capacity or the specific heat or the enthalpy of a reaction. It's something unknown. The other part is the environment. Now the environment is what we actually measure. It's usually very well defined and it's typically some type of fluid that we measure the temperature change of. So in our calorimeter, we have our environment and we have our system. And they both start out with their energies. And when they finish out, they're going to exchange energy with each other, but the overall energy of the calorimeter isn't going to change. Which means we get one very important relationship is that the change in energy, the Q, of both the environment and the system have to add up to equal 0. Or, in a more useful form, the Q in the environment equals the negative Q of the system. If the system loses energy, it has to lose it to the environment, and the environment has to accept all the energy lost by the system, and vice versa. If the system wants to take heat, it can only take it from the environment, and every joule of heat had to come from the environment. Now, typically, our Q, E, and V environment is well defined and is the same for every single experiment we run in a calorimeter. Typically, this is going to take the form that the Q of the environment equals the mass of the environment. So if you're using water as a fluid, it'll be the mass of the water, times the specific heat, Cp, times the change in temperature, delta T. Now what you're going to find is that Windows Movie Maker does not support Greek letters, so when you see a dt, little d, dt, or little dh, those are supposed to be deltas. I just can't put them in the videos. But that's our environment. Our environment, the Q is always defined as mass times the heat capacity times the change in temperature, at least at the general chemistry level. The question is, how do you define Q of the system? And this is going to depend on what you're looking for. Now, if you're looking for a heat capacity, Q of the system is going to look just like Q of the environment. We're going to have the mass of our system, such as a weight of metal or some material we're measuring the heat capacity of, times the specific heat, usually what we're solving for, and its change in temperature. Now, keep in mind, the change in temperature of the environment and the change in temperature of the system are two different numbers. You can't use the same number for twice. Sometimes they end up being the exact same value, but they are always, always, always unique to the material. Also remember that this change in temperature, delta T, is final minus initial. This is not the highest temperature minus the lowest temperature, it's final minus initial. Sometimes you'll end up with negative delta T's. That's fine. You have to in some cases because that accounts for the fact that if you have a hot weight in water, the hot weight got colder, so it lost heat, so its Q is negative, and the water got warmer, which means its Q is positive. So that's one scenario, you're looking for heat capacity. Second scenario is that you're looking for a heat of reaction, and this is always going to be Q-sis equals moles of a reagent or moles of whatever you're looking at times the delta H of reaction. Now, important thing to keep in mind when you look at systems like this is that the sign of delta H is going to tell you what the temperature change should have been for the environment. So if we have delta H greater than 0, this is an endothermic reaction. The system finished with more heat than it started with, which means the environment had to lose that heat. And so for any endothermic reaction, the change in temperature of the environment is always negative. It's always going to go to lower temperatures. For exothermic reactions, where the system finishes with less energy than it started with, we're going to have heat released to the environment, which means the temperature of the water is going to go up, or temperature of the environment is going to go up, and so our delta T is always positive. And these are your two scenarios, typically at general chemistry level. You're either trying to find the heat capacity of the system or you're trying to find the delta H of an unknown reaction. Now, if you're still having issues with enthalpy, go check through the video list. There's one on enthalpy. Also, feel free to look at more of the YouTube series here on thermodynamics. That should kind of get you started when it comes to calorimetry.